whatever kind of standards we have in place, there needs to be some kind of process for checking that the election equipment that's going to be used actually conforms to those requirements. This is the process of testing and certification. I'm going to explain briefly how it works in this segment. The majority of states have incorporated the federal guidelines and standards that I talked about in the previous segment. And the states that have require that voting equipment to be sold there has been tested for compliance by what are known as ITAs, or Independent Testing Authorities. The ITAs are a small number of approved private companies that specialize in things like testing. But there are a number of problems with this arrangement. One has to do with the incentives of the ITAs. In general, they're paid by the voting machine vendors for testing equipment and for producing reports to show that it's compliant. Since they want to please the voting vendors, they have a stronger incentive in a competitive market to produce a glowing report than a highly critical one. There's also a lack of transparency. The ITAs can have voting equipment submitted to them and then tested and find something's wrong. Well, at that point they can make a back channel call to the voting vendor and tell them to fix something, and then test the system again without releasing a public report. So in cases like that, even election officials might never learn about problems that, if they were security problems, they might be a close call or a sign that the internal quality of the product is poor. This lack of transparency just hinders effective decision-making by regulators. The final question is whether the kinds of tests that ITAs do under the standards are adequate for finding the kinds of security problems we've talked about in this course. And there is plenty of evidence that they are not. The kinds of testing that are required under current guidelines are what might be called conformance testing. This is fundamentally a checklist approach in which the testers go through the design and implementation of the system and make sure that it includes certain features and protections. Perhaps they also run some kinds of mechanical tools on the code to make sure that it has certain properties. But it's an inspection that's primarily focused on ensuring the presence of required mechanisms and features. There's another kind of approach to security testing, though, and this is what we might call open-ended testing. This is the kind of testing that researchers did in almost all of the studies you heard about in this course that revealed security problems. Open-ended testing is a simulated adversarial approach where the testers try to apply creativity and to think like an attacker, applying the security mindset to see if they can find any series of steps that would result in a compromise of the system. This is much more resource-intensive and more focused kind of testing, but it aims to demonstrate the presence of exploitable vulnerabilities rather than just to show that the system has complied with certain checklist items. Open-ended testing can be expensive. It's never going to be a guarantee that there aren't problems because the real attacker might be luckier or more resourceful or more creative than the testers. But it can be really good at smoking out some of the low-hanging fruit in any kind of insecure system, for getting problems that are going to be very easy for attackers to discover fixed before the system ships. This is something that's practiced widely in industry by some of the largest internet companies, and is something that's proposed in the 2007 draft VVSG guidelines. Now, comparing these two approaches, I will argue very strongly that open-ended testing provides much better security. But you don't have to take my word for it. Let's look at a historical example of the Diebold AccuVote touchscreen DRE. The Diebold machines were certified by an ITA that did this kind of conformance testing and approved for use in real elections. But then, when the machines were examined by researchers, we found a series of problems. Some of the early problems came out of the Hopkins report, which applied open-ended testing to find trouble with the code. Then Harry Hursty found more problems. The SAIC report found other problems. The Princeton report I was involved in found yet more problems. The California TTBR yet more, and the Ohio Everest study even more problems. And there are other examples beyond this. None of these problems were publicly disclosed in the process of ITA certification. So that just shows the value in finding security problems that can come from the kind of open-ended testing that's proposed in the 2007 VVSG draft.